Hello and welcome to the Edinburgh Science Festival. We're delighted you're joining us today for this event with Janna Levin, astrophysicist and author of the new book, Black Hole Survival Guide. Today, Janna will help us understand and find delight in the black hole, perhaps the most opaque theoretical construct ever imagined by physicists. You can get a copy of Janna's book through our festival book sale partner, Blackwell's. This event is free for you to enjoy thanks to our festival sponsors and supporters. Edinburgh Science is an educational charity. Please consider making a donation through our website to support the work we do.
Hi, I'm Janna Levin. I'm so glad people are tuning in for the Edinburgh Festival for 2021. I'm excited to be a part of it, to talk about my new book, Black Hole Survival Guide. I am an astrophysicist and an author, and I am also director of sciences at a cultural center in New York City, in Brooklyn, called Pioneer Works. And this is Pioneer Works here in the background. I'm also editor-in-chief of Pioneer Works' new online virtual assembly called The Broadcast. So I hope people will also tune into the broadcast, and where we have arts channels, science channels, a music channel, and a tech channel. Today I want to talk about Black Hole Survival Guide, and I'm showing you my wee little book here. I love this book. It's my fourth book. I love the size of it, which I thought was really sweet. It is very short. It's the shortest I've ever written. It reminds me of that Mark Twain quote, "I didn't have time to write you a short letter, so I wrote you a long one instead." And I think I had a long book, and I did indeed spend the time to try to make a very short book. It's very lean. One of the reasons I enjoy this book so much is because a dear friend and a well-known artist, Leah Halloran, an artist in California, professor at Chapman in California, an accomplished artist, painted 20-some paintings for me for the book. There's the International Space Station around the Earth, and they're quite beautiful. The actual original paintings are quite large, and they just do look spectacular in this book. Here's a little space-time diagram. Let me find you one of black hole. Here's some quantum wormholes towards the end of the book when we get into quantum black holes. Not the easiest subject in the world. And I really do think they add a lot to the experience of the book. And here's one of my astronauts who needs the survival guide, the tips in the survival guide to survive falling into a black hole. The book is, as I said, it's very lean. And I try to keep the reader and the language in a certain pace and a certain rhythm. It's not intended as an expository book. It's intended to really sort of flow and bring you in, but it's very abstract and very conceptual and kind of trippy in some ways. I want to shuck away some of the misconceptions about black holes in this book. And so I begin really with the misconception that a black hole is a thing. A lot of people have this impression that you come up to a black hole and you find a very dense object, but that is not actually the case. Sometimes black holes are formed by dense objects, but the dense object that forms the black hole actually cannot maintain itself. So there's this idea that was communicated with Einstein very shortly after he published his general theory of relativity by a friend who was working as an infantry soldier who was fighting in the war, had enlisted on the Russian front. And between calculating these ballistic trajectories, he's reading Einstein's paper in the Proceedings of the Prussian Academy of Sciences. And he sends Einstein this mathematical result, which decades later earned the name black hole. But it was really just a thought experiment. In the thought experiment, Carl Schwarzschild, who had made this discovery, imagined that all the matter of a star was crushed to a point and asked, what does space-time look like around crushed matter? And so that's why people mistake the black hole for being crushed matter. But the real importance was what Schwarzschild realized: if the mass is always in front of you, if as you approach, no matter how close you get, all of the mass is always in front of you, just in this fantasy, in this imaginary experiment, then what will happen is the space-time around the object will become so deformed that even the path of light not only can get caught into an orbit, but actually gets veers so close that it can't escape at all. In fact, it's forced to plunge inside the black hole like everything else. And this region where that happens, around this space-time, is what we call the event horizon. It really is just a part of space. It's just a region. It's not an actual thing. Now, the event horizon, what Schwarzschild realized, would cast a kind of a shadow on the sky because not even light can escape. And that's really what we mean when we discuss the black hole. We often really mean the event horizon. We start talking interior to that, our ideas get rather murky, and we really aren't quite sure we're on steady ground. Now, this was really just a mathematical solution. It described how you could orbit around this region in space-time, how light would travel. It was quite beautiful, and Einstein really appreciated the mathematics of it, but he really believed that nature would protect us from their formation. Einstein believed that there would be no way to actually, in the universe, create black holes. And it was quite a surprise that in the decades that followed, really many decades of people struggling to understand nuclear physics, making breakthroughs in some cases because they were working on nuclear weapons in the 40s, in the late 30s and 40s, and they realized that the nuclear forces that were at work burning thermonuclear fuel, like a series of hydrogen bombs inside stars or other nuclear bombs inside stars, would eventually run out of fuel, and the stars would begin to collapse. Now, they argued for a long time whether they would collapse all the way to what we now call a black hole, or whether they would just create a very dense state of matter. And what was realized that if the star was big enough, that it would be unable to support itself against its own gravitational pull, against its own weight, and it would collapse all the way to making an event horizon. Now, if there was a star 10 times the mass of our sun, it would have to get to 60 kilometers across. This is from millions of kilometers across to 60 kilometers across. It's actually city-sized at this point. Then it becomes so dense that it creates the event horizon. The space-time is almost like a waterfall falling inwards. Even light can't escape. You'd have to travel faster than the speed of light to escape this waterfall. And light becomes dragged in. But that applies for the star too. I said black holes are not dense objects, and now I'm talking about dense objects. But what happens is once the event horizon forms, the star can no more stay there at the event horizon than it can race outward at the speed of light. Its only option is to continue to collapse and get smaller and smaller and smaller. And then what happens to it, we're not 100% sure. So the collapsing star leaves behind it this imprint, this archaeological record in space-time that we call the event horizon. And there's nothing there anymore. So if you were an astronaut and you were to try to drift up to the event horizon, to where this star had finally made its last appearance, not even the light radiating from the star can escape anymore, all of it falls inward, you would find nothing, empty space. You could drift across the event horizon as though nothing terrible was happening. And so that's what we mean when we say a black hole is in some sense more like a place than it is a thing. It's more like a space. It really is a space-time. And that is fundamentally different than any other object in the universe. And that's why I like to say black holes aren't really things. Now, sometimes they behave a lot like things. They can move around and orbit each other. And so they can behave, they trick us sometimes. But really, they're just an empty region of space-time. Quite spectacular. Now, in the singularity, when in the very center, what we call a singularity, after the star collapses and it continues to collapse and it gets smaller and smaller and denser, we don't really know what happens to it. It is theorized that maybe there's a region that becomes infinitely curved as a star is forced to continue to collapse. It has no other choice. And a singularity be a region essentially that we think the laws of physics seem to fail. The elements of the star would rush towards a singularity, which now literally is like a cut in space-time. And to some extent, as far as we could tell, would simply fall out of the universe and cease to exist. Now, Most people don't believe that that happens, and that we just don't understand the quantum forces when things get that dramatic. And so that's a lot of the book, is picking that apart. So that's really where I want to begin in this story. And then from those chapters, we can make our way through understanding space, through understanding time, through understanding the actual astrophysics of black holes that we see, and then to the kind of real imaginative theory of what is beyond even Einstein's theory of gravity. I like to begin at the beginning with readings. So this is chapter 1. Black holes are nothing. Black holes are special because there's nothing there. There is no thing there. I probably accepted black holes whole, as complete conceptual entities, before I was able to doubt, before I had intuition to combat. They were fodder for fantasy. I received the fact of their existence without resistance. Gullible and without prejudice, I could see their plausibility, appreciate the curiosity, their peculiarity, accept the universe as it was presented. Maybe it was the same for you. It's very unlikely that this is your first encounter with the astrophysical oddity that is a black hole, the warp in space-time so strong that not even light can escape. I don't know what it was like where you were, but I had a pretty unspectacular view, astronomically speaking, out of my childhood window. I would edge to the foot of the bed and strain to look at the sky through the window frame, a portal to a green yard below, the seams between neighboring plots demarcated by shrubs or trees, patchwork real estate scooped together under a rounded cap of atmosphere. The ground would darken first, then the trees, but the dome would hang on to the vaguest splattering of light for the longest. Ours was not an urban burnished sky, but still light pollution diluted the view that I stared into night after night. I never expected the vista to improve or anything new. Only the usual indistinct few bright speckles like rain stains on a windshield. I don't remember when the feeling started, the first time that longing tugged at me, but before I even recognized the desire, I pined to know what else was out there, like a restless dog pacing at the door. I wanted to be free of ordinary confines, to fly there and explore. Frustrated by the fact of the heaviness of my feet on the earth, I wondered, striding at the base of the sky, restless to be let in, I wonder how many of us inherited this longing, millennium after millennium, generation after generation, child after child, bound to the crust, wrapped at the illusion of a ceiling, compelled to crack through and define our puniness and our limitations. I'm skipping ahead a little. Black holes were a purely mathematical construct on the page, benign in virtual form, in typescript on paper, unverified for decades, unaccepted for decades, absurd, maligned, and denied by some great geniuses of the 20th century until physical evidence of real black holes in the galaxy was discovered. Find one just a few thousand light years away, a light year being the distance light can travel in a year, nearly 10 trillion kilometers, the distance you would travel driving at the average highway speed limit for 10 million years. Take a left at that yellow star and veer toward that star cluster. Wandering at the base of the sky, we are under them. We are above them. Black holes in their abiding darkness are scattered plentifully among the stars, which themselves are scattered plentifully, like somber glitter infiltrating the void. We are in orbit around one in the center of our Milky Way galaxy. We are pulled toward another in the Andromeda galaxy. I want to influence your perception of black holes, to shuck away the husk a bit, get closer to their darkest selves, to marvel at their peculiarity and their prodigious character. We can take a road less traveled, follow a series of simple observations that culminate in an intuitive impression of the objects of our attention, which are not objects at all, not things in the conventional sense. A friend takes me out in New York to discuss the essentials to include in a black hole survival guide. An accomplished science writer, he asks me to clarify, don't I already know everything about black holes? Do you know they are nothing? He looks at me, unblinking for a long time, considering. He pauses to toss some salted peanuts into his mouth, and while chewing, he says, I guess I don't know anything about black holes. Then, slightly bemused at this realization, we eat the rest of the bar snacks and drink our wine while we talk about things more familiar. So thank you so much for indulging me in a reading remotely. After chapter 1, we get right into the science. Chapter 1 is very short. These are all very short chapters. Chapter 1 is really just to build in that sort of personal tone and the phrasing of the book. And then we get into the hard stuff, what space-time is. And it's not a chronological or expository trip. It's really just a trip of thought experiments. I really like to think of these as journeys. Like we take these mind journeys first to the concepts of space-time, to the concepts of the fact that black holes distort space-time so much that when you come to the horizon, the edge of a black hole, if you left your astronaut companion behind you safely on the International Space Station, that space and time would be so distorted between you two that what your astronaut that you left behind believes to be the center of the black hole, a place in the center of a sphere, for you, once you cross that horizon, looks like it's a point in time, looks like it exists in the future. And so as you fall, as you cross the event horizon and inevitably fall in the way the star that formed the black hole continued to fall towards that singularity, as you fall in there, you will feel as though you're falling towards your future. You could no more avoid the singularity in the center of that black hole than you could avoid the next moment in time. And so we know that while it surprises people, you could actually cross a black hole quite happily. You could drift across the event horizon and not even really know it was happening. You might see light distorted very strongly around you. And in fact, it wouldn't even be dark inside the black hole. That's one of the other fascinating aspects that I like to dispel. Black holes are dark from the outside, but they can be bright on the inside. So if the light from the galaxy falls in behind you, you could see a big bright flash of light as you make your way towards that singularity. And ultimately, you will in fact meet your demise in the center of a black hole, because eventually, as you approach its singularity, it will become so strongly curved, so devastating that your ligatures are ripped apart, you become flayed, you become crushed. Eventually, you're torn into your own quantum bits, and your own quantum bits disturb the space-time around it, because the space-time is so reactive, it's so strong in such an extreme state that even your own quantum particles become an influence. You create a kind of a storm in space before we don't really know what happens to you. And so there is a great deal of current contemporary physics, theoretical physics, devoted to understanding what actually happens to your information, the facts about you, the details of your quantum particles inside the black hole. And so the final chapters are really very much about that. And it is a fascinating tour because it's going to change how we think about the universe. Black holes are teaching us on this terrain by showing us how extreme and frenetic and challenging the gravitational physics is at that point, that it's giving us clues as to how to understand a theory even beyond Einstein's. Now, even if you stay safely outside, stay safely outside a black hole, it can be quite interesting out there too. Black holes can have these tremendous jets. They're like ray guns. I give you a lot of tips on what to avoid in case you actually do encounter a black hole. But in addition to this very abstract theoretical importance of black holes, they astrophysically have seen an unbelievable century already of discovery, of real life discovery from two black holes colliding, ringing space-time so strongly that if you were floating nearby, the squeezing and stretching and deformation of space could conceivably ring your eardrum, and you would actually hear the collision, like hearing a ringing drum, even in the vacuum of empty space. That discovery led to a Nobel Prize. Recently, just a couple of years ago, the Event Horizon Telescope project took the first human-procured image of a black hole ever. And I think a lot of people are surprised to know that we have never seen a black hole before this. We've seen the indirect consequences of black holes tearing apart companions, creating dramatic jets, sculpting the galaxies in which they live. We had never actually seen the shadow of the event horizon against a bright backdrop. And that is what Event Horizon captured. It was really quite spectacular. The black hole that they captured is 6.5 billion times the mass of the sun. Yet, and that sounds very big, it's solar system sized, which is actually tiny for its heft. The whole point of black holes is that they're spatially tiny for their heft. And so this spatially tiny black hole, just the size of our solar system, is 55 million light years away in a neighboring galaxy called M87. And resolving this shadow, think about pushing that so far away. Resolving this shadow was this tremendous technological challenge that took a telescope effectively the size of the Earth. It was equivalent to resolving something the size of a piece of fruit on the moon. And so congratulations to the Event Horizon Telescope team. I was there at the National Press Club in Washington, D.C. when the announcement was made. It was very moving, very exciting. I felt this moment when the entire world froze to take in the image of a black hole together. 1 billion people tuned in to see that. So it was quite this sort of moment when we realized across the globe, this is an international effort, and not only scientifically, that the results are shared freely with the international community, and that in this one moment, we all realized, that whole perspective. There we are looking together at this enigma in the sky. So thank you so much for tuning in. I'm actually very excited to take questions. I think that's going to be the best part of this experience. And I'm really grateful to everyone who's with us today. Thank you.